Dear students, now let's begin with the calculation of 10 dq or measurement of delta O. That can be measured by using DD transition. We know that when electron jump from T2G to EG orbitals, some energy is released and that energy is that it definitely helps to find the value of delta O or 10 dq. A band or bands in the absorption spectra can be related to the excitation of electron from T2G to EG orbital. Now, when from this DD transition value, we can find out the value of delta O. So, we can define 10 dq. It is 10 dq is the energy difference between T2G and EG orbitals. That is, it is the energy required for the excitation of electron, for the excitation of 1 mole of electron. In this electron jump from T2G to EG, that energy difference or energy required for that excitation of 1 mole of electron is nothing but the 10 dq. This value we can calculate by using the equation 10 dq is equal to, which can be also called as energy, is equal to N into H into C into nu. Here N, it is nothing but Avogadro's number, which is 6.023 into 10 raised to 23 mole inverse. H is Planck's constant, whose value is constant, that is 6.63 into 10 raised to minus 34 joule second. C is velocity of light. Its value also we know, that is 3 into 10 raised to 8 meter per second. Wave number, this value, it is given. So, for example, now let us consider that the absorption band due to DD transition in one of the complex, it is 20,000 centimeter inverse. That means nu its value is given. So, we can calculate 10 dq. So, 10 dq, it is nothing but, first we will put the Avogadro's number value, then Planck's constant, this is the Planck's constant, then velocity of light. Here we are taking velocity of light in centimeter because the absorption band value is given in centimeter, and nu its value, it is 20,000. So, we can do the calculation, and after calculation, this is the value of 10 dq, which is in joule, and if we convert it into kilojoule, the 10 dq value for the wave number 20,000 centimeter inverse, it is 239.58 kilojoule per mole. So that much energy is required for the excitation of electron if the difference between or the DD transition value, if it is 20,000 centimeter in. So in this way, we can calculate the 10 dq value. Now, the next part which we will discuss is factors affecting the value of, see here, this part we will discuss now, factors affecting the value of 10 dq. Just now we discussed how we can calculate the value of 10 dq from DD transition. Now we will discuss which are the factors which affect the value of 10 dq. The magnitude of delta O or 10 dq in the octahedral complexes depends on, first is nature of ligand, then it also depends on the charge on the central metal ion, and as well as the position of this metal ion in the transition series. It depends on these three factors. Now let's begin with all the three factors. First, we will discuss how it depends upon the nature of the ligand. Now, it follows that the value of 10dq or delta O increases with increase in the strength of the ligand. That is, if the stronger the ligand, more is the splitting and more is the value of 10dq. Now here you can see these are the complexes of chromium, and when we go down, the strength of the ligand is increasing. All of you know chlorine is a weak ligand while cyanide is a very strong ligand. So as the strength of the ligand increases, the absorption band increases. At the same time, the 10dq value is also increases. So we can say that 10dq or delta O, its value depends upon the nature of ligand or the strength of ligand. As the strength of the ligand increases or stronger the ligand, more is the splitting. Here splitting is more, and as splitting is more, the energy required for the excitation is more. So 10dq value is more. Next is charge on metal ion. Now, as CFT is based on the electrostatic model, the charge on the metal ion has a direct effect on the value of 10dq. Now, it can be explained in two ways. First condition is different charges on cation of same metal. It follows that the value of 10dq increases with increase in the charge on the ligand, that is metal ion with the high charge. High charge means metal ion, it should be of smaller size. If ligands are having higher charges, if the metal ion has higher charges, it produces more splitting and hence more is the value of 10dq. So here you can see here, metal ion is same, but charges are different. In first case, the charge is +2, and in second case, the charge is +3. These are the example. So in second case, as the charge is more on the central metal ion, the 10dq value is also more. It is given in the centimeter inverse. Okay. Now, next is charge on metal ion, but here we are considering the second condition, different charges on cation of different metal. Here metal ion is also different and charges are also different. See here, if two different cations with different charges and has same electronic configuration with same geometry, then cation with higher charge has higher value of 10dq. See here, two complexes are given. One is for vanadium and another is for chromium. Metals are different. They have different charges. On vanadium, there is a +2 charge and on chromium, there is a +3 charge. But they have the same electronic configuration or both possesses D3 system. So it is said that the cation with higher charge has the higher value of 10dq. Here you can see chromium has the higher charge and hence its 10dq value is also higher. That means more splitting is there. Now, third situation is same charge on cation with different electronic configuration. I'm sorry, here it should be +2. Now, in this type, 10dq value decrease with increase of d electron. Here, the number of d electrons are more. Now, see the example. This is a cobalt complex and it is a nickel complex with same ligand. Both these possesses same charges, +2 +2. Only thing, in cobalt it is a D7 system, while in nickel it is a D8 system. So, more the number of electron in d orbital, lower is the value of 10 dq. So, cobalt with D7 system has higher value of 10 dq, while nickel Ni2 plus with D8 has lower value of 10 dq. Okay. Now, see, third, position of the transition metal ion, or the row in which the transition metal ion is placed. Now the value of 10 dq is increases with, or as we goes down to the group from row 1 to 2 to 3 in transition metal series. See here, CO3 plus, rhodium 3 plus and iridium 3 plus. They form the complex with the same ligand. Their charges are also same. What is the difference? Only their position. Cobalt, it is present in 3D series. That means first row of the transition metal. Rhodium, it is present in 4D series. That is the second row. And iridium, it present in 5D series. That is third row. So, as we go from first row to second row to third row, the 10 dq value is also increased. So, these are the factors which affect the value of 10 dq. First factor, what we have discussed, nature of ligand. So, what we had seen, as the strength of the ligand increases, the 10 dq value increases. Second, we had seen charge on the metal ion, that we had discussed in 3 formats. One is, if the central metal ion is same, but if charges are different, then more the charge, more is the 10 dq value. Similarly, second condition was, if metals are different, their charges are also different, but with same electronic configuration, then here we have seen metals are different, charges are different, but with same electronic configuration, then the metal ion with higher charges has higher value of 10 dq. Another situation we had discussed here, metal ions are different, cations are different with a different electronic configuration. Then in such situation, the metal ion with more number of electron in d orbital has lower value of 10 dq. And the last one, as the number of the row increases from first to second to third, if the position is different, then the value of 10 dq increases. That means the metal ion which is present in 5D series has higher value of 10 dq. Okay, so these are the factors affect the 10 dq or delta O value in octahedral complex. Thank you.